guest today is Chelsea Finn. Chelsea is one of the world-leading researchers in artificial intelligence and robotics. After completing her undergraduate at MIT, she did her PhD at Berkeley, where she was co-advised by Sergey Levin and myself. From there, she spent a year at Google and became professor at Stanford. Her PhD research made pioneer contributions in robot learning, meta-learning, few-shot learning, and won the highly prestigious ACM Doctoral Dissertation Award. As professor at Stanford, she continues to lead the charge in artificial intelligence and robotics research, and she has won many awards, including the MIT TR35 Innovator Award, the IEEE Robotics and Automation Society Early Career Award, the ONR Young Investigator Award, faculty awards from a wide range of companies, including Microsoft, Intel, and Samsung, as well as many Best Paper awards. Aside from being one of my own favorite researchers, turns out Chelsea is also a listener's favorite. We have been asked many times to try to get her on the podcast. Chelsea, before diving into today's conversation, I'd like to thank our podcast sponsors, Index Ventures and Weights and Biases. Index Ventures is a venture capital firm that invests in exceptional entrepreneurs across all stages, from seed to IPO. With offices in San Francisco, New York, and London, the firm backs founders across a variety of verticals, including artificial intelligence, SaaS, fintech, security, gaming, and consumer. On a personal note, Index is an investor in Covariant, and I couldn't recommend them any higher. Weights and Biases is an ML ops platform that helps you train better models faster with experiment tracking, model and data set versioning, and model management. They are used by OpenAI, NVIDIA, and almost every lab releasing a large model. In fact, many, if not all, of my students at Berkeley and colleagues at Covariant are big users of Weights and Biases. Chelsea, so great to have you here with us. Welcome to the show.
Thanks, Peter. Happy to be here.
So glad to have you on. Well, Chelsea, AI has made a lot of progress over the past decade. Training large neural networks on large amounts of data has enabled unprecedented capabilities in visual recognition, speech recognition, natural language understanding, even decision-making, with beating the world champion in Go, playing video games, and even robots learning some basic skills. What can AI not do yet today?
That's a great question. I think that there's been tremendous progress in machine learning and AI in some of the applications that you've mentioned, but there are also still a lot of real-world use cases where it's challenging to successfully deploy machine learning systems. And one of the reasons for this is what's called distribution shift. This is when the data that the system sees when it is deployed is a little bit different from the data that it was trained on. So, for example, a robot that was trained to do a very simple task like picking up a cup in a lab environment, if it's then asked to pick up a cup in a slightly different environment or pick up a slightly different cup, that's a little bit different from what it was trained on, and it won't naturally generalize to the new situation. Or another example that we can probably all relate to is spam filters. In our emails, in our inboxes, the emails that we get from spammers change over time, and spammers often actually try to actually evade the spam filters that are trained with machine learning. And as a result, the data is changing over between when it was trained and between when it's actually being used. And as a result, it doesn't act as successfully as we would hope it to.
So this distribution shift seems like it would be almost everywhere. Pretty much nothing is completely stationary in the real world.
Yeah, absolutely. So first, the real world is changing all the time. And second, we also often want to deploy systems in different parts of the world or in different situations. So as a result of this, this kind of distribution shift comes up all the time in different real world applications. And unfortunately, we don't currently have great tools for actually tackling it. So I think that one of the most common tools to use in industry is just to try to keep on training on the most recent data that you've seen. But that ends up being fairly laborious, requires labels for the most recent data. And so some of my research is actually trying to address these challenges by trying to just improve the generalization of these systems and also allowing systems to just generalize to new parts of the distribution by being more robust immediately or making it possible for these systems to be very quickly adapted to new parts of the distribution, either adapting on the fly themselves or making it easy for practitioners to be able to have tools for kind of editing the behavior of these models.
Got it. Now, when you say you're trying to address this in your research by making the models more robust or allowing for editing, can you dive a bit deeper on that? It goes well beyond just continuing to train. There's some fundamental change to the models you're proposing.
There are a few different techniques that we've been exploring, and one of them is kind of some of them are targeted at certain kinds of distribution shifts. So one specific kind of distribution shift that comes up all the time is when models latch on to spurious features. So an example of this is something where, say you're trying to classify objects in an image, oftentimes actually the object is highly correlated with the background. So you might be trying to classify between dogs and wolves, for example, and dogs will more often be on like grass or something like that, whereas wolves might more often be on snow backgrounds. And oftentimes then when you train a model on this kind of data, it will actually pay attention to the background of the image in order to make the classification, rather than paying attention to the actual object that you're trying to classify. And so we've developed techniques that actually try to encourage the model to pay attention to the correct features of the image and not rely on these spurious attributes. That's kind of one set of approaches. And then the second set of approaches we've been looking at is allowing them to adapt on the fly more easily. And there's a whole range of approaches that I guess I could talk quite a bit about. Some of them are more specific to robotics, and I guess some of them are more specific to kind of general machine learning systems.
Let's start with the more general machine learning ones. Yeah. How does it work to tackle this problem?
Yeah. So let's see. Even within the general machine learning systems, there's lots of different approaches. But I guess one that I'll talk about is we've been looking at making it possible for a practitioner to quickly edit a model. So one classic example that we've been bringing up is if you ask a language system, who is the Prime Minister of the UK? If it was trained just a few years ago, it would probably tell you the answer is Theresa May. And that's actually a few prime ministers ago and is quite out of date. And we'd like to be able to make a targeted edit to this model without having to fine-tune the entire model, without having to retrain the model, because a lot of these models are actually quite large, and fine-tuning them or retraining them, first, it can be computationally expensive, and second, it's somewhat of a blunt tool. It will update all of the weights of the model, and it might update the model in ways that you don't want to, because there are other parts of the model that are doing just great. And so we've been developing techniques that allow practitioners to make a very targeted edit to the model by actually basically training what we call a model editor that can edit a very specific function of the model without touching the other functions of the model.
Okay, that sounds pretty interesting. Can you elaborate a little bit? What kind of data do you need? What happens to the model?
Yeah, absolutely. So we've been taking a meta-learning approach to this, and we've essentially been we collect a small data set, much smaller than the data set that the original model was trained on, that gives it examples of how we want to edit the model. So for example, in the prime minister setting, we may want to tell it that if I ask you who is the prime minister of the UK and tell you to edit it in a specific way, then you should also edit the behavior of the question of who is the PM of the United Kingdom, or other versions of that, like is Theresa May the PM of the UK? And once you have a data set that has these examples of edits and also the kind of examples that aren't related to that edit, then you can train this small model editor to be able to make targeted edits to the model. And that model editor can take a couple of different forms. One approach that we've taken is to have the editor actually directly change the weights of the model with a rank 1 update to the model. rank 1 update to each of the weights makes it such that we don't actually have to output something that's as large as the entire weight vector of the neural network. We can actually output something much smaller, and then it kind of expand it. Another approach that we've been taking is a more non-parametric approach, and that's something where we actually store the set of edits that we want to apply to a model, and then when we're given a new input, we try to judge whether or not that input is in scope for any of the edits that we want to apply. And if it is, then we have a separate model that will take care of that new input. And if it's not in scope, then we'll just ask the original model.
Interesting. Now, when you are considering things in scope, out of scope, it seems like that itself would have to keep changing over time too. Is there any way to somehow automate that process? Because now maybe next year something else has to go out of scope and something new has to come into scope.
Yeah, so predicting whether or not an edit or an input are kind of within the same scope is actually a fairly simple problem. It's just a binary classification problem to tell, are these within the same scope or not? And so actually the beauty of that second approach is you actually just need to kind of maintain this memory of edits that you want to be applied to the model. And that is fairly simple to do. You can simply add things to that memory or remove things from that memory if it's kind of no longer applicable as things are changing over time. The other thing that you could do is, and we actually haven't done this ourselves, but it's something that we've thought about, is you could actually, if your bank of edits that you want to apply to the model has grown too large, you could actually kind of distill it into the original model with a fine-tuning like approach, and then kind of flush that memory and start over with a new set of edits. And so in this process, when you want to make an edit, the edit is really, really fast to the model. You just need to add something to that kind of memory bank of edits. And the kind of scope classifier that tells whether or not something is in scope, and the other model that kind of handles the edits, kind of applies the edits, those only need to be trained once for all of the edits that you might want to apply.
Do you think you can possibly automate some of this? Let's say you kind of mine the internet for more novel data, right? Things that are timestamped at a later date than the things that your model was trained on, and somehow maybe say everything that's from a later timestamp from a reliable source, if it contradicts something the model already thinks or knows, it should be allowed to overrule it. So it's kind of a different kind of training where the later things somehow get to overrule the earlier things.
Yeah, absolutely. So one thing that we're actually currently working on right now is essentially allowing one of these models to try to read the news, like you're mentioning, like read things that are more recent from the data that it was trained on, and then try to figure out what has happened and what contradicts my current beliefs, and then try to actually automatically generate the edits that should be applied to the model and update the model accordingly. And so that's something that we're currently working on. I don't know of any approaches that can really handle that problem effectively right now, but I think it's a really exciting direction and something that should be possible because people can kind of update their knowledge by reading the news as well.
Very interesting. Now, earlier you said that there are some methods for dealing with distribution shift that are more applicable in kind of general machine learning, others that are more specific to robotics. What do you do in robotics that's different?
Yeah, absolutely. So I guess first, this kind of editing, in principle, we've been focusing on language models in that work, but in principle, it could be applied to really any sort of machine learning system, including robotics applications. But in robotics, I think that there's something that is a little bit special that we can, that sort of makes the problem easier in some ways. So robotics is an extremely hard problem, but one thing that's a little bit different from standard machine learning is the system is actually interacting with the world, and it's making multiple decisions, not just one decision. And because of that, it can actually collect a little bit of its own data, both during training, of course, but also during testing, and it can affect the observations in the data that it sees. And so in robotic settings, one of the things that we've been looking at is seeing whether the robot can adapt to a new situation on the fly. And that might mean maybe it kind of attempts the task once, doesn't quite succeed. But if it fails at the task, that doesn't mean that it's done. From there, it can actually from there, it can actually retry the task and try a new strategy on the fly. And this is something that people do all the time. If you're trying to like put a key into a door to open your front door, it might be a little bit tricky to get the key in on the very first try. But that's no big deal if you can't. You can just kind of try again with a slightly different strategy, maybe push slightly harder or orient the key slightly differently. And that means that these systems, they don't have to be, in principle, they don't have to be quite as robust when they're making these decisions if they can adapt on the fly. And so we've been developing approaches that in robotics allow kind of the robot to try again and to try slightly different strategies. Maybe a priori, it actually learns a couple different strategies for the task, not just one strategy. And second, actually allowing it to adapt. And that could mean that it takes a couple different trials. Although more realistically, these robots, we want them to be able to adapt on the fly autonomously. And so that means they actually need to figure out how to retry and figure out how to retry from the state that they ended up in after they failed. So that actually also introduces somewhat of a challenge as well.
It seems like if a robot were to fail, as you said, it'll introduce a challenge because it's now in a state it might never have encountered during training, because during training maybe it mastered how to do this. And now it has to somehow deal with an even bigger challenge that it's in a very unknown territory to recover from, to then do another attempt. How do you deal with that?
Yeah, so this is actually a really huge challenge that I think is underappreciated in a lot of robotics and machine learning. So as a specific example of this, say that you have a legged robot and maybe it was trained to kind of navigate a building or navigate a certain scenario to get to some goal or to deliver something. And then maybe something has changed. Maybe there's an obstacle in the way, or maybe there's something on the ground that it didn't see before. And at test time, when it's in that new situation, maybe it like flips over, or maybe it kind of ends up on its side or ends up in a position that it's never seen before. This is really, really challenging because if it had never seen itself flipped over, for example, then now it doesn't have any data that tells it what to do when it's flipped over. And it actually needs to learn and kind of collect data on its own and explore in the new environment in order to figure out what to do in that situation. So first, it's a really hard problem. But second, it's something that we've started to make some strides towards. So first, it's something where you really, at test time, you shouldn't just be running a policy. You shouldn't just be executing what you learned during training. You need to actually be learning and updating the kind of the neural network policy as you go. And second, you may also need to be doing some exploration. So if you're in a very new state, you may need to actually not just be kind of greedily acting with respect to the policy that you're updating, but actually also taking somewhat exploratory actions. And one kind of key insight that we've seen so far is trying to take exploratory actions, not just in general, not just kind of taking random actions, but taking exploratory actions towards the data that it has seen so far. So trying to get back to the data that it's seen. And that seems to work a lot better than just trying to explore in general, because then you'll hopefully move towards the data distribution that you know well. And from there, you should be able to kind of complete the task and continue to make more progress.
Yeah, I was actually watching a talk you gave about that just yesterday, and I thought it was really intriguing. There's a lot of work that has been done where human data is used as a prior to stay close to encourage more interesting behaviors of the agents as they explore the world. But it seems in this work, what you're doing is you are actually looking at the agent's own past experiences and somehow saying staying close to your own past experiences should be good as you encounter new situations. What's the intuition that it would also apply there?
Yeah, so I guess the agent's own prior experiences, if it has learned the task before in a previous situation, then I think that that's the kind of the part of the data distribution where it knows how to act, where it knows how to succeed. And so staying close to the data distribution is generally a good idea because that's exactly where it was trained. And so this is kind of a principle that we've been looking at for this sort of adaptation. It's actually also just generally a more general principle. So in this whole subfield called offline reinforcement learning, where you want to be able to train a robot from an offline data set, generally the key principle there is also trying to stay within the data distribution that it saw during training. And by doing so, it's actually these algorithms are much more successful at being able to learn from offline data without any sort of online interaction. And I think it's just generally a pretty successful principle for robotics.
Kind of have maybe taking one step back. We want to go beyond what's seen in the training distribution, ideally, generalize beyond. But fundamentally, I guess I'm curious, do you think we can even hope to generalize beyond the training distribution, in the sense that how can we learn about things that we haven't seen? Where does the juice come from if you want to generalize beyond the training distribution?
Yeah, it's a great question. First, I'll say that there are some kinds of distribution shift that are just impossible to handle, especially if the system is only given one opportunity or one chance to do it. Or if maybe you're deploying a robot in a new scenario and it's a really safety critical scenario where it makes a mistake and it kind of causes a catastrophic failure. There are definitely scenarios where it's simply impossible. And I think that actually part of the research challenge is figuring out what scenarios are impossible and what scenarios are kind of scenarios that we can make headway in. So that's one comment. Another thing that I think is worth noting is that in order to handle these kinds of settings, we do need to go beyond some of the standard assumptions in machine learning. The really common assumption in machine learning is that the data is kind of independently and identically distributed between training and testing, and that we have samples from that distribution. And a lot of the work that we've been doing on trying to make models more robust is introducing some additional assumptions. Like maybe you have, maybe you know, for example, maybe you have a medical imaging system and you wanted to deploy it in a new hospital that is never seen before. And in your training data, actually, maybe you know the hospital that each of the parts of the data distribution came from. And in that scenario, you can actually leverage the hospital labels to actually make your model more robust to handling a new hospital. By actually, for example, training a model to be invariant to whether it's from hospital A or from hospital B. And so we introduce these new assumptions that allow us to actually improve generalization in very specific circumstances. So that's a circumstance where if you go to a new hospital, it could be still that's impossible because the new hospital it does things in a completely different way from all the previous hospitals. But there is something that we can say about the generalization, like if the hospital isn't too different, if it kind of comes from the same kind of meta distribution of hospitals as what we saw during training, then we may actually be able to generalize beyond the training distribution. So yeah, first, there are some things that are impossible. Second, there are some additional assumptions that we can introduce. And then lastly, like we've been talking about, I don't think we have to necessarily constrain ourselves to this train test paradigm that's common in a lot of machine learning. If we actually continue to train during testing, as a robot experiences more data, or as we get a little bit of unlabeled data from a distribution, for example, then we may be able to kind of get beyond the fact that we're seeing stuff that's completely new.
Very interesting. Recently, you, I think, coined this term. I hadn't seen it before. Single life reinforcement learning. What is that?
Yeah, so this is actually like very similar to what we were talking about before. So essentially, we've been thinking about how if we want a system to adapt in a new environment at test time, and it has some previous experience, we want the robot to be able to learn on the fly in the new situation. And we want it to be able to do so without interventions, without any sort of kind of reset of the environment, without a human necessarily providing kind of giving help to the robot if it gets stuck or something like that. We want the robot to be able to do the task in kind of a single life or in a single episode. And the other thing that's different about this is that typically in reinforcement learning, there's this trial and error process. So the agent or the robot will attempt the task once. It will then kind of get reset to some situation and then attempt it again. And it'll repeatedly try to perform the task over and over again in order to eventually get a policy that's very successful. And so the outcome of that process is this policy that can do the task and can reliably do so. And this makes a lot of sense in like a factory setting where you want to be able to do the task over and over again. However, there are a lot of scenarios where you don't need a policy to be able to do it over and over again. You just want the robot to do the task once. And so maybe it has a lot of experience doing a certain task. Like maybe, for example, you want it to navigate a building in order to find something in the building. And it has some experience doing that in the past. Maybe you want it to find something new, or maybe something has changed about the building. You don't need it to kind of repeatedly, again, kind of run this reinforcement learning process. You just need it to be able to go into the building in this new scenario and retrieve the object once. And so this is what we're calling single life reinforcement learning, where it has one life or one episode in order to do the task once. And its goal is to do it successfully and ideally as quickly as possible.
So as a single life, but am I understanding correctly, the single life refers to, in some sense, the evaluation time, but before that, it can do a lot of training to be ready for that single life, single episode evaluation run.
Sort of. So it does have to do with evaluation. In the problem setting as we defined it, we just said that it gets some prior data, some prior experience, some offline previous data. It doesn't get to kind of collect specifically try to collect experience. And I think that the other crucial thing is that at test time, it's in a new situation that it hasn't seen before. And so it's going to have to learn. And so it's not just that it's going to be deploying a policy at test time in this one life. It actually needs to continue learning throughout the reinforcement learning, throughout this kind of single episode or single life. And this is pretty different from the standard reinforcement learning setting.
You've done a lot of the leading work in deep reinforcement learning over the past several years. And in reinforcement learning, typical formulation is that an agent is requested to optimize a reward function. And the more reward that gets collected by the agent, the better the performance of the agent. For example, scoring the game or something, task completion for a robot. Then I'm watching your talk at Carnegie Mellon just from a couple of weeks ago, and I found you saying, I actually don't like reward functions. What do you want instead?
Yeah, so I think that in the real world, reward functions are extremely unrealistic. The real world doesn't just tell you if you're doing well or not. For example, like it doesn't tell me if I'm doing good research, or it doesn't tell a college student whether or not they're doing a good job. Maybe grades are a proxy for whether or not a student is doing a good job, but they really aren't kind of a great indicator of whether they're kind of, I don't know, happy and doing a good job at handling everything that's coming at them. And so, and if we want to train a robot to do something, to pour water, for example, there's nothing that tells them whether or not they're doing a good job of that either. So I think that they're not something that actually comes naturally in the world, and it's something that the reinforcement learning problem statement assumes. I don't think I fully know what the alternative should be. I think that task specification and generally communicating goals to robots is a really underrated problem in reinforcement learning and robotics, because it's not even clear how it should be formulated even. If I were to use a reward function, I think that kind of sparse 0-1 reward functions, like you succeeded or you didn't succeed, is probably the best type of reward function, because that is kind of much less ambiguous, fairly unambiguous, compared to something that tries to evaluate a more fine-grained notion of progress. I also think that ultimately it'd be awesome if we could tell robots in natural language or with gestures how we would like them to complete certain tasks. And in the long run, I think that kind of natural forms of communication are the ideal way to communicate goals and tasks to robots.
And in fact, you've done some work on that, where agents learn to understand what it means to open or close a door. Can you say a bit about how that works?
Yeah, so we have some work. I guess we have a few different things on this, but we basically have some work where if the robot has collected some data, you can use crowdsourcing to label the data and say, what was the robot doing? Or if you were to tell the robot kind of an instruction for this behavior, what would that instruction be? And so something like that, I think crowdsourcing is a promising way to try to collect annotations for this because it's pretty scalable. And then from there, once you have those annotations, then you can learn something that maps from a video to those annotations, and you can use that to essentially either learn some form of reward function or try to simply maximize the probability that that the label will correspond to the desired goal or the desired task. So this can essentially be a way to derive reward functions without assuming that they're just given to you. And then once you have that, you can use your favorite reinforcement learning algorithms or planning algorithms in order to actually optimize for the behavior that you want.
It seems if we could have such a fully general reward function, if this was trained on a very large amount of data, maybe then reward functions could become actually pretty useful.
Absolutely. I think so. Yeah. One of the huge challenges with reinforcement learning that makes this a little bit difficult is that the algorithms are going to be optimizing against them. And so it's going to be trying to optimize for the parts of the space that the reward function that you've just learned will give you a yes, will give you success. And this means that if there are any holes or any parts of the data that the reward function hasn't been trained on, then the optimizer can often find it. And so this can make things a little bit tricky because maybe it's trained on a lot of data, but it's not trained on all possible behaviors that the robot might try to do to trick it into thinking that it did the correct task. So they need to be quite robust. That said, there are also tools for trying to kind of prevent this sort of exploitation of the reward function as well, like using ensembles to estimate uncertainty or something like that.
Yeah, I find this direction really interesting. And I'm also pretty hopeful about this direction because, for example, in generative models for image generation, GANs have been very successful at image generation and follow there's a bit of a similar two-player game. There's a generative model, a discriminator. The discriminator corresponds to the reward. In fact, you wrote one of the early papers making that analogy in reinforcement learning with what happens in GANs. And it seems like once you have enough coverage, but maybe that's the challenge here. Once you have enough coverage, the discriminator might be pretty good.
Yeah, so I think that these sorts of adversarial optimizations, kind of two-player optimizations, are quite a promising approach for this. And we're using those kinds of approaches in our research as well. But as you said, covering the entire space, I think, could possibly be intractable. I think that there are just so many possible behaviors that are out there. I mean, there's obviously all the behaviors that humans do, but even that is only a very narrow set of the space because humans do things with a very specific purpose. And when a robot is trying to learn something, they'll be waving their arms out around in the air randomly, or be doing things that are just very strange. That are very different from what humans would ever do. So as a result, I think that covering that entire space can be very difficult. This is also a reason why exploration is very difficult as well, because exploration, if you try to explore every possible behavior that is out there in the world, then you may not actually ever end up on the one behavior that the one sequence of actions that will actually lead you towards the right thing. And so I do think that I think that these sorts of adversarial optimizations are promising, but I also think that it's worthwhile to try to investigate approaches that don't require you to cover the entire space. And so, yeah, that's something that I always keep in mind when developing these kinds of approaches.
One thing I've been wondering recently, I'm curious about your thoughts on this, is it possible we're just not training long enough? And the reason I'm asking that is because if I look at our 3-month-old son, I mean, he's not doing the most directed things in the world. He's already three months in. Granted, he doesn't have to because we'll provide food and we'll provide everything for him. But it still seems like very few people have the patience to have their robot run for 3 months plus and still see essentially almost nothing all that adult meaningful happen and just keep going.
Yeah, absolutely. I have a lot of thoughts on that. I think that first, part of it is, we need to have a lot of patience. I also think that a lot of reinforcement learning algorithms do need a lot of supervision. So reinforcement learning offers this promise of being able to allow robots to autonomously learn things. But in practice, oftentimes a person needs to be there and reset the environment kind of back to where things were. Or if the robot knocked an object off the table, a human needs to kind of come and pick it up. And arguably, some of these things are things that parents do as well for kids. And so some of it is somewhat unavoidable. But I also think that, my guess would be that the kind of the typical robot learning algorithm, often it needs actually interventions like every 10 seconds. Or maybe if you're lucky, every minute. And I think that that's a lot more frequent than parents do, if we're to kind of continue the analogy. And so I think that first we need more autonomous systems so that we can run them for longer. And so this is something that we've been working on a lot, is improving the autonomy of the robot learning process. And then the second thing is, I don't think we need to necessarily rely fully on online data collection. And I think that the robot learning community has been for a while kind of stuck in this place where for every project we do, we start from scratch. We don't reuse any prior data. We kind of collect a new data set for that project from this particular setup. We learn on that data set. And from this standpoint, I think this is really problematic because you're never going to accumulate 3 months of data within the context of a single project. If you have enough resources and have enough robots, maybe you can parallelize it and do that to some extent. But in general, it's going to be pretty impractical. And I think that if the computer vision community had to recollect ImageNet every paper that they wrote, I think that we wouldn't have made nearly as much progress as what they do right now. So I think it's really important to be storing data and actually having algorithms leverage previously collected data and build upon that, and have that previously collected data, that offline data, be growing over time, and ideally something that people are sharing across institutions as well.
And actually, you have collected several of those larger data sets yourself and in collaboration with other institutions. Maybe you can list them out.
Yeah, so we've had some initial attempts at this. So one of our first attempts was, or I guess my very first attempt was when I was doing an internship at Google, and I collected some data of kind of a robot randomly pushing objects around in this gray bin. I put the data out there, and it was used a tiny bit for some kind of video prediction benchmarking. And then after that, we expanded the data and collected some data at Berkeley. This was with Frederick Ebert on with kind of these Sawyer robots. And both of these data sets were kind of pretty different from a lot of the existing data sets because they had lots of objects and lots of diverse interactions, and they were quite large in size. But they were still only on a single robot, usually in a single environment. And so then from there, we I had just moved to Stanford, so we collected data at Stanford, we collected data at Berkeley, we collaborated with some folks at UPenn, and we also combined it with the Google robot data. And so we had data from at least 4 different institutions and across 7 different robot platforms. And that was our first attempt at really trying to share data across institutions. And people have been using that data a little bit. But one of the kind of challenges we realized there was that it was all fairly random interactions that were fairly hard to learn from as well. You couldn't just use imitation learning with the data. And so then more recently, we collected what we called the bridge data set, where we're collecting data on these low cost arms. It was all demonstration data. So it's all really high quality data. And it spanned multiple different environments, although it was all collected at Berkeley. So this was in collaboration with Sergey at Berkeley. And that one, I think, has made kind of significant strides since RoboNet. And then more recently, I've been thinking that we really need a larger effort to really get a much larger set of environments. So the bridge data set had around like kind of order of 10 environments. And if someone else wants to use it at a different place in a new environment, I think that generalizing from 10 environments to an 11th environment is going to be pretty hard. And so I think we need something more like thousands of environments. And so one thing we're working on right now is we've kind of formed a kind of a coalition of researchers at several different institutions. And we want to actually have people take home robots and take robots home and then collect data in something closer to kind of 1,000 different environments.
Can people who are listening to this contact you and volunteer to take a robot home and collect some data?
Possibly. I think that if they're in the area of one of the institutions that we're collaborating with, then certainly.
Oh, very cool. Now, switching gears for a moment, the model agnostic meta-learning, or MAML paper, is one of the most highly cited papers in artificial intelligence. It's very rare to have such a successful paper, even for the most accomplished researchers like you. Do you recall how that paper came about? And at the time, did you think it would be such a big paper?
Yeah, so it kind of came about through conversations with Sergey, and I don't fully remember all of the conversations. I certainly was frustrated that we were training robots from scratch for every task, and I thought that we thought that one initial way to do that is, instead of training them from scratch, maybe we could kind of have some set of pre-trained weights and be able to quickly adapt those weights. And Sergey and I had a number of conversations about this around the idea, and I think that Sergey was the one who proposed the kind of this initial technique for avoiding training from scratch, actually in the context of Q-learning, which is actually one scenarios where MAML was actually really terrible at. And we figured out a really simple scenario that we could test it on, which was this kind of sinusoidal regression problem, like a 1D regression problem, really, really simple. And I think I was working on something else at the time, and so I didn't really want to spend that much time on it, but I spent about a day coding it up and running it, and it seemed to work on the first try. And so that was a good sign. Whenever anything works in research on the first try, that's usually a really good sign. And so because it worked on the first try, I decided to pursue it a little bit further, try it on Omniglot and other few-shot learning problems. And then I also spent actually a lot of time trying to also extend it to some reinforcement learning problems. And then regarding your second question, I knew at the time, I was definitely very excited about it at the time. I was pretty excited about it, and more excited about it than some of my other projects. And so I could tell it was something that was larger than my other projects. And I could tell that it was something that seemed to work really well because it worked on the first try. I don't think I necessarily knew how big it would be. And there certainly have kind of since then been projects that I've also been kind of really excited about as well. Although they haven't yet had that much time to have impact. So I think that I could tell that it was going to be a successful paper, and it was something that I was really excited about it, but I didn't know, I certainly didn't foresee people using it for all the different applications that I've seen people use it for.
I'm curious, we're several years since the paper was published, right? And it was one of the early meta-learning papers. Meta-learning is learning to learn, right? How do you personally see the trajectory of meta-learning from the MAML paper to where it is today, and maybe where it'll go in the future?
Yeah, so it's been a pretty interesting trajectory. I also teach a course on meta-learning, and so I try to keep that up to date every year. I think that in meta-learning, I think that there are really three broad classes of methods that have been kind of quite successful. The first is kind of black box methods. This includes some very early work by Adam Santoro et al., the RL squared paper that Rocky was the first author of, that you co-authored, and Jane Wong's paper that was a kind of applying these RNNs for meta-learning. second class of approaches is these optimization-based ones that kind of MAML is a part of. And then the third class of approaches is things like prototypical networks and matching networks that are more kind of non-parametric in nature. They try to kind of compare examples. And so those are really, I think, three of the most impactful, I think, classes of works. Since then, I mean, certainly there's been like a ton of works that have tried to make each of these classes of approaches better in different ways. And seeing all of those works has been quite interesting. And then there's also been works that have tried to analyze the use of meta learning in different applications. We've seen that meta learning may not be that important in few-shot image classification settings because it's really a lot about feature learning and less about actually learning to optimize. We've also seen that, and so, yeah, there was that. We've also seen kind of a lot of different applications of this. I think that one application that I've heard people being excited about, although I don't know that much about, is drug discovery, where you want to be able to use this on different possible drug candidates and adapt it with a very small amount of data for a new drug candidate. We've also been using it in education domains as well, where you want to adapt to new curriculum or adapt to new instructors or new exams. And then I think the most recent wave that we've seen few-shot meta learning be kind of a hot topic is in the context of large language models and in-context learning. And I think that this is in some ways kind of a revival of some of the black box approaches that we've seen where you have kind of a neural network that's kind of learning from a few examples. And the thing that's been different and new and exciting about this approach is that it seems like this few-shot learning is emerging without explicitly training it to do few-shot learning. You essentially train it on this unstructured data, like Wikipedia, and then it seems like it can do that without explicitly setting up the training data in a certain way. And so there's also been some work analyzing why that happens, the scenarios in which that happens. So yeah, I think that that's kind of a rough trajectory of where I've seen things. There's also some pretty exciting work on learning optimizers as well, and trying to learn optimizers that are very general and can like outperform Atom or something like that.
Now, I like the way you described the evolution. I remember at some point I gave a talk about meta learning, and Jürgen Schmidhuber was in the audience, and he essentially he called me out, like he likes calling people out, and he said, "Look, if it's only one time learning to learn, it's not really meta learning. It needs to keep recursing. It needs to learn from there to learn, and keep repeating this kind of somewhat acceleration." And I personally haven't really gotten any handle on how to do that, and haven't seen as much work in that space either compared to what you're describing. I'm curious about your thoughts. Have you seen anything on that front?
I guess first, when you brought up Jürgen Schmidhuber, I thought you were going to mention kind of the work prior to the kind of the evolution that I mentioned. And I guess, of course, I should mention that kind of prior to these three classes of modern approaches, there was also a lot of work in the late 80s, early 90s on meta learning that actually introduced somewhat similar ideas, although it's really looking at the ideas and less at seeing some of the, I think, kind of exciting results that we've seen with the more modern approaches. But specifically for your question on this more recursive form of meta learning, I don't think I agree that that has to be a requirement for these algorithms. I might refer to that more as like meta learning and meta learning. I guess I haven't seen anything on that front that has been particularly exciting, although I guess I'll mention a couple of things. One is that there was a work, I believe by Luke Metz at Google, where they learned an optimizer, and then they actually showed that the learned optimizer could be used to optimize itself. And that was something that was, I think, kind of cool and a little bit mind-twisting. And the second thing that I'll mention is I sort of think that meta learning can be viewed as learning on different timescales, where the few-shot adaptation process is this really short learning period, and the meta learning process is at a slower timescale where you're actually trying to learn priors about the world. And from that perspective, I could certainly imagine something that learns at more than two timescales, that learns at kind of different intermediate levels of timescales as well. But I'm also not sure if there's a lot of practical value um, from kind of going even more meta. And I certainly haven't kind of directly observed kind of practical value or myself from this sort of thing.
Curious, when you look ahead, what's your vision for what'll happen in the next, let's say, 5 to 10 years in artificial intelligence?
It's a good question. I think that, I mean, one trend, of course, has been that we've seen larger and larger models. We've been seeing people train more and more general models. And especially in large language models and generative models, and vision language models. And I think that that has actually been a very exciting trend. For example, the GPT-3 paper was exciting for me because it showed something that was far more general than a lot of the other machine learning systems that we've seen that are pretty specialized for the tasks that they were trained on. And so I expect to see that trend somewhat continue, to try to build larger models and see what they're capable of. Um, I also suspect that the I suspect that data plays a really massive role in these systems, and so I suspect that or I at least hope that we'll see systems that, or techniques and tools for understanding how the data affects the system, and tools for curating data sets, and tools for understanding understanding different parts of the data set. And in robotics, I think that we're actually in a regime, and this actually relates to one of your earlier questions, where I think we're in a regime where we're quite data limited right now. I think we do need much more data in robotics. I think we are not training on nearly enough data because first, we're generally training on data sets that are smaller than NLP and computer vision data sets. And second, I think that robotics is actually a lot harder than a lot of the classic NLP and computer vision problems. It requires a lot of precision. It is a very high dimensional system. And so I think we're going to need more data than what we need in those other settings. And so in robotics, I hope to see a push towards larger data sets that are open source and released, and a push towards improving the generalization of robots leveraging those data sets as well.
That definitely resonates. Now, I'm curious, where did you grow up? What kept you busy as a little kid? And how did that all get you into artificial intelligence?
Yeah, so I grew up in California, about an hour east of where I am right now. I really love California. It's a place where you can do lots of outdoors things all year round. And yeah, the weather is great. As a kid, when I was younger, I really liked doing jigsaw puzzles. And yeah, getting better at that and solving that. I did a lot of different things. I played trumpet, and started doing that in 5th grade, and was in the wind ensemble, was in the kind of marching band, in high school. And yeah, I really liked making music. I also did some sports. I played some soccer, and I also did a fair amount of swimming, and I swam competitively in high school, as well. And then I also actually, in middle school and in 5th grade, I was on a Lego robotics team, which was trying to build these robots out of Legos and do a set of challenges within a very short time period. I think it was actually like a 2.5-minute time period that you got to have the robot do all these sorts of different things. And it was my first exposure to debugging. I distinctly remember a moment in 5th grade where I went up to the coach of the team and I told her it's not working. And what should I do? And she told me that I should figure it out. And I had this kind of aha moment of I can actually I don't know what the solution is, but I can actually, instead of just asking someone for what the answer is, I can actually try to think through it and try to figure it out. And so, yeah, that was a fun experience as well. I didn't really at the time know that robotics would be a big part of my career, but it was something that I enjoyed doing. Apparently, I also bossed around a lot of the guys on the team. I think there were 5 guys on the team and me, and the coaches. They never told me this. They never called me this when I was there, but apparently, the parents would all call me the general because I wouldn't tell everyone else what to do on the team. And since then, I've tried to adapt my leadership style to be a little bit more kind of compassionate, I think. Yeah, so those are some of the things that I did, yeah, when I was growing up.
Yeah, I'm curious how that you think, like, what triggered your, like, right now, obviously, you're very focused on AI. Where do you think that kind of transition happened from what you described as a very wide range of activities that you were doing to really zone in on AI as such a big focus for you?
I started learning how to code maybe in 8th grade, and I really enjoyed that. And I knew that I wanted to go into engineering because both my parents were in engineering, and I got this sense that engineering was all about solving problems and puzzles. And I knew that I liked trying to solve problems and puzzles. Uh, when I got to college, I basically applied to schools that I thought were good in engineering. And I also really liked biology in high school, and so I was considering biological engineering. But as soon as I got to MIT, I got the sense that electrical engineering, computer science was a department where I mean, first would be trained you get a really good engineering training, and it's also just like a really great department at MIT. But I also got the sense that it's something that you can, it opens a lot of doors, and it's something that you can take in many different directions once you understand computer science and electrical engineering. And so, I knew that if I wanted to do bio later into the future, I could do that with a CS degree, or an ECS degree. Whereas if I did biological engineering, I probably wouldn't be able to go into other paths. And so that got me into, from there, I was kind of pretty sold and kind of pretty eager to do ECS at MIT. And then from there, in terms of the classes that I was taking, I was never really that interested in some of the more systemsy classes. And I was really just fascinated by how you might teach a computer to see and how you might learn from data. I thought the machine learning was really just seemed like a fascinating concept, and also computer vision seemed like a fascinating concept. And so I took 3 computer vision classes as an undergraduate, I think all of which were graduate level classes, starting in my sophomore year. And from there, I did a little bit of research as well. And yeah, I got the sense that AI was just a really cool area. It also involved kind of probability and various forms of math, which I enjoyed as well, and found a little bit kind of intellectually deeper. And then from there, when I was applying to PhD programs and ultimately at visit days, I got the sense that robotics was an area that I was particularly excited about, because you were going all the way to like really the end system and the end goal, which is to get a physical robot to do something. And it's also something like that's really rewarding to see if you can actually get the physical robot to do something.
Well, I would agree on that front. It's a beautiful story. Now, it's easy to forget, but you're actually still very early in your career, as in you're recognized as one of the leading AI researchers, but actually your PhD started about 8 years ago. You did it pretty quickly in about 4 years. And now you're a professor for only 3 years, and you've done so much already in so little time. So I'm curious, are there any productivity tips you can share?
Um, I mean, I think my biggest tip is to work on things that that you're excited about. I think that, at least for me, if I'm excited about something and I find it interesting and I find it intriguing and I enjoy doing it, then it doesn't even feel like work. It doesn't feel like I'm necessarily being productive. It feels like I'm exploring something and learning something and doing something that I enjoy doing. And so that's certainly how I've felt about AI research, and coding up things like MAML. And I still try to every once in a while code up a small idea. So yeah, I think that that's probably my number one thing, is yeah, for me trying to do things that I enjoy doing.
Doing something you enjoy allows you to bring a lot more energy to it, right? Now, one of the things that also stuck with me from your PhD days is that I think you went swimming pretty much every single day. Do you think that also improves your productivity overall?
Yeah, absolutely. So I really enjoy swimming as well, and so I like doing things that I enjoy doing. I think that swimming does a number of things for me. In addition to just enjoying doing it and also I usually swim with other people, and so it's a social activity as well. But I find that exercise is very good at stress relief, and so it helps me reset. And if there's something that I am stressed about for whatever reason, even if it's not a good reason, after I go swimming, typically I'll be less stressed about it, and that can help me focus on the things that matter, rather than dwelling on the things that I shouldn't be dwelling too much on. Um, and then I also think that I don't know, being in good health in general, is good, and it helps me sleep. I think sleep well at night. I think that days I don't swim or the days that I don't exercise, I usually have a harder time going to sleep, because I'm just less tired. And I suspect it also helps with energy levels, although I don't really know. Um, I haven't really done that many controlled experiments with it. I also don't drink any coffee or anything, so yeah, I don't know. Oh, I guess the other thing that I'll mention is I also, like, try to sleep, like, 8 hours a night as well. I think that that was really important, and in undergrad, I think I was pretty good at sleeping, enough, but I definitely found in grad school that if you don't sleep enough, you can't, like, at least I didn't I found that my brain wasn't good at the work I needed it to do, and so, and yeah, making sure that you're treating your body well is generally important.
There are so many students out there in the world that their hope is to join your lab for their PhD, or maybe join your lab as an undergrad researcher or as a volunteer and so forth. What do you look for when you recruit students?
Yeah, it's a great question. I mean, one thing that I look for is, I mean, it's good to have research experience. I think that there's some amount of research experience, and the student is eager to do a PhD, then that suggests that they can be successful at research in the future, and that they know what they're getting themselves into as well. Um, Another thing that I look for or look into a lot is the letters of recommendation that they have. If there's someone uh, who can say great things about them, then that means that they're probably a great person to work with, and they're someone that, um, yeah, a great person to work with, and someone enjoys working with them, and so forth. Um, and then I guess one other thing that I sometimes look for is, kind of eagerness to work with real robots as well. I find that there's so many applicants that are really excited about machine learning, and there's a smaller set of applicants who have worked with real robots and are excited to continue working with real robots, and also really get that same, um, that kind of equal, that also find it very rewarding to work with real robots and to see a real system work. Although I often find that students don't exactly know exactly what they wanna work on during their, when they're applying, and so I've had situations where I've had 2 students come in. One I thought was going to be really excited about working with robots, and one that I thought was really excited to do more algorithmic work, and it turned out that it ended up being the complete opposite. The one I thought was going to do algorithmic work, he actually ended up being really excited about working with robots, and the other person, she ended up being really excited about doing more algorithmic work. So, um it's yeah, those are some things. It's also just really hard to evaluate applicants, just by looking at kind of their application, and even, like, after talking to them for 30 minutes is also pretty hard. So, it's a noisy process, and so I also, I think it's good for students to apply to lots of different places, because there are also just, like, so many really amazing, labs out there that are doing really cool work.
Maybe one last question. Do you have any advice for, let's say, high school students who are probably still too early in their career to join a research lab typically? What are some things they can maybe do on their own that could guide them into an AI career in the future?
Yeah, that's a great question. I mean, certainly when I was in high school, I was swimming and in marching band and not thinking about AI. And so I guess first I don't think students need to have it all figured out in high school. It's good to have kind of a rough idea for what you want to do and a rough plan, but also to understand that things will be a little bit different and things won't go according to plan and so forth. Um, and then I think that beyond that, um, I do think that there are, yeah. opportunities to learn a lot of stuff just online. When I was in high school, I don't think that things like YouTube really existed at the time. I certainly didn't know about them at the time. But now there's all sorts of resources online for learning how to code, or learning a little bit about machine learning, or learning about probability and statistics and so forth. And so I guess the first thing that I would say is trying to learn the basics, trying to learn how to program, and trying to learn how to debug things, make things, and so forth. And then from there, I think that beyond just learning the basics, also, if there are opportunities to do projects and get your hands wet, and or get your feet wet, and actually try to build things and try to explore. Robotics teams, I think, are great. Yeah, I think that actually just trying to do projects and trying to take them on is a really great way to explore something, because first you'll learn a lot through the process of trying to build it. Like if you try to build a spam classifier or something like that, you'll learn a lot about the process that isn't necessarily taught in courses all the time. And then you'll also learn this really useful skill of debugging and trying to solve problems on your own that I think will be extremely valuable in the long term.
Thank you, Chelsea. This was such a great conversation. Thank you for joining us.
Yeah, happy to have joined.
Thanks so much for listening. If you enjoyed this conversation just as much as I did, please give us a thumbs up, leave a comment, put a rating. It'll help other people find the show. Thank you.